Now, in this lecture, we will consider section 4.4.3 Energy in Dielectric System. We know about that when in electrostatics we do work in bringing the charge, then it stores electrical energy in the field or in the system. Now, what will happen to that energy when dielectrics are introduced in that system? So we know from our chapter 2 that the electrostatics work done is half CV square in case of a capacitor, where C is the capacitance of the capacitor and V is the voltage which develops across the plates of a capacitor. Now, this is a capacitor without any dielectric material. So when we place a dielectric material inside this capacitor, then its capacitance will become, the C will basically become is the dielectric constant or the relative permittivity times the C vacuum or the C free space. So its capacitance will increase because this epsilon R is greater than 1 and for all the materials. So this will increase the capacitance of the capacitor and it will ultimately increase the energy stored in a capacitor. So for the energy inside in electrostatic system, we are having energy in terms of W. This is equal to epsilon naught or half epsilon naught and then E square integrated on the whole volume. This is the energy stored in an electrostatic system, and E being the electric field here, epsilon naught E square. Now what will happen when we fill the capacitor or the system with a dielectric material, then this will become W or the energy stored in the presence of dielectric will become half, and then epsilon naught will be replaced by epsilon naught epsilon R and E square d tau. So here let me write the integral and E square d tau here. Now the question is that the energy has increased of this electrostatic system by epsilon R here. Epsilon R is greater than 1. Now, how this energy has increased? This is a question. Means the dielectric basically increases the energy of the system. How the dielectric increases the energy of the system? Because polarization occur in this dielectric, and that polarization basically stores electrical energy, and we will have to sort out this thing. Now, from where this energy comes in, we will have to explore the concept of charges, the concept of bound charges, because when a dielectric comes in action, then bound charges come in action, and that changes the electrostatic system energy. So it means that we will have to incorporate D here, because D is epsilon naught E plus P. It is accounting for the polarization, and we will have to introduce D here as well, because E is the overall picture. E is not accounting for the E is having inside that one the rho F and the rho bound, but when we will incorporate D there, D will account for the free charges, and then the polarization will come in action, and we will have the equation will basically change from this to this, to half d dot e and d tau. Now how this one changes from this equation to this equation, in this section we will discuss this thing. So let's start from the concept of the charges here. So we know that work is basically the charge times the voltage V here. So EV, energy or work is equal to this. In an integral form, I can write that this will be integral and rho d tau for charge, and then V here with this one. And further, I can write this thing that because there are two things, rho equal to rho free and rho bound. Now what is rho free? Rho free is basically the charges that we are providing, we can control from external, while rho b is the material factor, the bound charge which is inside the material. So we cannot control this one because it depends on nature of a material. So externally we can control this one. So basically, when we connect the system to an electrostatic system, then we are bringing free charges here, and we are only controlling this one, not this one, because it is the result of these charges. When they come in, then the bound charges are the polarization basically occur here in the dielectric material. So let's say we start up bringing this rho f into a small segment, like a very small charge that we bring here to the system. So I can write this expression now, that W is equal to integral, and this I will call a change, a slight change in the energy of the system, and this I will write rho f and V and d tau. And now I know from my previous the Gauss's law for this one, that d dot dA on a closed surface integral is equal to rho f, the free charges. So from here I can write that in a differential form I can write this one, that okay, this is qf, the charge, free charge. So from the divergence of d in differential form I can write this one is rho f here. So this I can write for a small change here, is this will imply that divergence of a small change in D is equal to small change here in rho f. So I can replace this small change in f with this one, and del w will be equal to del dot small change in d and v d tau. Now I will have to exploit one identity here, and that identity is that if we are having a vector like the divergence of any vector A, and it is with the it is with another, let's say, let me write b here, b being a scalar with this one. So divergence of a b, then this is equal, this can be written is divergence of this, divergence of a in v plus a dot gradient of v. So then I can write this thing is this will be equal to del w equal to integral, then divergence of a, so a is here or this vector quantity and this is del d and v d tau, and plus this will be another integral and a is del d dot gradient of v here and d tau here. So gradient of v and del d tau here. And now if I do this thing, if I do convert this one to a differential form, means with the help of a Stokes theorem, divergence theorem, this one, then I know that if I take the volume integral and it is divergence of any quantity, for example, we are having a vector quantity v and it is in d tau, then it is the same if I take a closed surface integral and I take v dot dA. So I can convert this one easily here. So this will come out to be, this will imply that this is equal, this one is equal to del d integral the change in d dot dA, change in d dot dA. So here we are having the gradient or the divergence of del dV. So we will also come with this one, and I can also write this thing is equal to closed surface integral is here, closed surface integral, and del the change in d and v dot dA. Now this term basically vanishes to zero, and the reason for this one, that if we take a closed surface and we increase its surface area, means it's a big surface, then what will happen, the d or v both drops to 0 at infinity, at very high value here. So this term basically goes to 0 and we are left with this term, which is del the change in energy, and this is equal to del d means the change in D. And for this one, gradient of V, I can replace this thing with E, because here the gradient of E, I know that the gradient of E is equal to minus del V. The negative gradient of potential is the electric field. But I'm not considering the negative sign here, because the negative sign is only for reference, that we are bringing the charge from infinity to that point. So I can write that this is E, E and D tau here. So change in this in E d tau here. Now this relation applies to any material. But if I consider a dielectric material, then for the dielectric material, I have D equal to epsilon E, where epsilon is the permittivity of that medium. So I can write this one. Now what I need here, so for D, I can write epsilon E here. So what I need to find out this thing, that what del